Raiden, Zach, Preston, Rockford. Oh, Sam, Jonah, Elizabeth, Wes, Dylan. Nice fall day. What?
Fall had to come back for a week.
Yeah. Usual for like the first snow to stick around as long as it did. With chat, put that open. All right, come on, camera, do your thing. All right, same bit about right there. Let's see. Got some homework this week about. Hello. Got some homework this week about induction, and we'd like to spend some time today maybe looking at the homework and kind of shifting the focus as we head from 33 into 34, shifting the focus very specifically to, we'll talk about induction, we'll continue to do so, and maybe some other concepts, but we're going to really try to put the focus on the fields. So Faraday's law is pretty naturally written in the language of magnetic flux and electric potential, or magnetic flux and voltage. We'd like to kind of shift and put the focus on magnetic field and electric field. And I think we've one question in the homework that is like that, kind of section, I think 33.6. The very end sections of chapter 33, there's two sections about inductors, which I think are 33.8 and 9. We will talk about inductors, but I think we're going to do that more when we get around to talking about chapter 35, which is AC circuits. So we'll hold those off a little bit. But that's an inductor is a circuit element that we're going to see appear in some of our diagrams going forward, along with batteries, along with resistors and capacitors. Yes, Maxwell's theory of electromagnetic. So that's what I was looking for. There it is. Okay. So I think we'll do that. That's what I'm going to look for is which questions from the chapter are from 33, 6, and 7. That is question number 17. Right, that was one of them this week. 17, I think. Then 36 is a different one. Okay, yeah, 17. I think maybe do one question here. To get started, just think about this a little bit. How do people feel with the homework? And we'll get some questions about homework. Are there ones people would be curious to see a little bit of feedback about? Putting it on DocCam. So this is what I mean. It's circuits that have inductors. We'll talk about those, but maybe not for a little bit. One I was kind of curious to talk about would be something like 27 might be a good one to just kind of practice our thinking. Figure 33.27 shows a 10 by 10 centimeter square. So the original wire, when flattened, would be 10 by 10 square, but they've put a 90-degree turn in it. So it's kind of a 5 centimeters turn, 5 centimeters along the maybe like the up, down, right, left axes. A uniform magnetic field points downward at a 45-degree angle. What's the magnetic flux through the loop? Let's maybe just kind of try to do this here. How would you think through this? Well, it's a uniform field, so we don't have to do so much maybe like that. So much of like an integral, but we could just multiply, or I mean, do a dot product to find the flux. Flux is a dot product of magnetic field with the area vector. So first of all, what's not the answer? Here's probably not going to be the answer for maybe one of a couple reasons. It's not going to simply be, you know, like the full area of the loop, which is kind of 10 by 10. You know, like 0.1 meters times 0.1 meters is 0.01 meters squared. It's not simply going to be 0.01 meters squared times the magnetic field strength of however many Tesla. Maybe for a couple reasons. How would you go about finding the magnetic field through this? Usually we've had flat surfaces, right? You know, like a circular loop, a rectangular loop. I think there might be one like with a triangular loop, but flat, maybe something like over here, we'd say like, what's the flux through that inner ring? I think is perhaps what the question is about on number 38. But how would you guys do 27? Get out some paper. Ways to go about it. Five centimeters, and 10 centimeters into the page, 45-degree angle for the magnetic field south of east, let's say. So I think I'll sketch something like that out. Maybe just do kind of a flat end-on view, 5 centimeters. Another 5 centimeters. And we'll just kind of understand that into and out of the page, there's 10 centimeters. And then the magnetic field direction could be, magnetic field, and I think this was 0.50 Tesla, which is still actually pretty decent in size. What do you guys do? You could kind of deal with it as kind of like two separate surfaces and find the flux through each of the two panels and sum them up. And that would work pretty well. If you wanted to do that, you could think of this as maybe like, this could be panel 1, and then my area vector for number 1 is kind of like, this is my area vector for number 1, and then this is my area vector for number 2. And how big would those areas be? I think in magnitude, they'd be the same, and they would both be 5 centimeters in the, 5 centimeters in the plane of the page and 1/10 of a meter perpendicular to the page. So what is that? Bring it down a step, 0.005 square meters. And then we can just do our dot products. We could do this. This would work pretty well. If it's uniform, we can basically do B dot A. I guess we are doing a little bit of an integral. I mean, slightly, because we're just breaking it into 2 pieces and then dealing with each piece. Maybe we can do like this plus this. And actually, although A1 and A2 aren't the same vector, the angle that magnetic field makes with each of them happens to be the same vector. So this would be BA1 cosine theta 1, BA2 cosine theta 2. But what are theta 1 and theta 2? Theta 1 is like this angle right here, and theta 2 is kind of like this angle right there, red to green, red to green. So they're both 45. Not that they'd have to be the same, but if I think in general, what if you imagined kind of leaving the loop there and kind of changing the direction of the magnetic field around? I think these would always add up to 90. You know what I mean? but you could imagine like, what if this had been the, maybe I should have put a 45 degree in here, somewhere it kind of implied like this is 45 degrees kind of from the vertical. I think these would always add up to 90, but you could make it more efficient for hitting the left panel and less efficient for hitting the top panel, or kind of somewhere in between, more the other way. So what do we get here? B A1 plus A2, what we get times the cosine of 45 degrees, which is, you know, like square root of 2 over 2. A1 plus A2 would be the full area of the loop if we'd flattened it out. So I think we get 0.50 Tesla. The full area does end up being 0.10 meters squared, which is 10 centimeters times 10 centimeters. But then we pick up a factor of cosine of 2 over 2. And whatever that comes out to be, well, we would have gotten 5 times 10 to the minus 4, and then we multiply that by this decimal, which is about 0.7, so it's about 70%, 71%, I think. And we get 3.5 times 10 to the minus 4. And the units are Tesla meters squared, and Tesla meters squared is Weber. Everyone gets a unit named after them. Faraday. Oh, that's Farad. Sorry, not Faraday, but Farad for capacitance. Volt, Coulomb, Newton, Joule. What else we got? Tesla, Weber. Inductance, which is the key number you would need to describe like a coil. An inductor in a circuit is measured in capital H Henry. Amps, forgot that one. Amps, ohms, how could I forget ohms? Watts. Everyone gets something. I mean, if you were like a scientist doing electromagnetic work in the 1800s and you don't have a unit named after you, you were pretty kind of average dude. One guy who doesn't, though, is Maxwell. And he gets a whole set of equations named after him, but he didn't kind of come up with any new concept. He just pulled together all the pre-existing concepts that other people had introduced in different and important ways. What's another way? So this was kind of breaking into 2 flat panels, because like I like flat panels and my thing isn't quite flat. What's another way you could kind of have thought this through? I'm gonna kind of maybe almost like put this back in. What's another way you could kind of thought this through? Anyone kind of go about it differently when they just first saw the sketch on the book page? The full area is like, you know, double of this number. The full area is 0.01 meters squared. But what's really important about this arrangement is what? How much area does it present from the point of view of the magnetic field? Like if you're riding along with the magnetic field, this doesn't look like a 0.01 square meter panel in front of you. It looks like how much? Something less than that. And all that really matters is kind of like, all that really matters is kind of like that distance or that area if you multiply it by 10 centimeters into and out of the board, because all we really want to know is how much area perpendicular to the magnetic field does this loop present, does this object present. So it's probably this dimension times 10 centimeters. Well, what is this dimension? This is 45 degrees, 5 centimeters, 5 centimeters. This dimension would be 0.05 meters. And then again, we would pick up like a factor of square root of 2. Instead of picking up a factor of 2, which is like the total length of the green stuff. The green stuff perpendicular to the red stuff is the square root of 2, whereas the total length is times 2. So we're down by an amount. So this is, you could call this something like Let me put another factor on here of 1/10 of a meter. I could call this something like, this is kind of like A perpendicular, and that's not the greatest notation actually, but what do you think I mean by A perpendicular? You can kind of tell what I'm going for here. Probably I'd be a little careful. I might want to call that A parallel because depending on how you think of it, you know, like this would be the parallel component of the A vector, something like that. Anyways, that's what's going to matter. I think from this point of view, the minimum flux for this arrangement would be if the field was like this or like this. And then actually, I think this is probably about maximum flux you could get for this shaped object if you had a uniform field coming at it.
Tried another couple of angles, it is.
What's that?
I tried another couple of angles, just adding them together, and it is the maximum at 45.
So you kind of went over to here and you used different angles, like maybe 30 and 60 or.
I just used 40 and 50, and it was slightly less.
Yeah, so you know, if let's say that theta 2 is 90 minus theta 1, which is going to be true for this shape piece of green stuff. So what's cosine of 90 minus an angle? Sine of the angle. So this would end up being like cosine plus sine, and you could just kind of ask yourself, what's the maximum or minimum values of like cosine plus sine? Maybe even in particular, like as you range from 0 degrees to 90 degrees, where they're positive, you don't have to worry about negatives, but negative would just kind of mean we're kind of hitting the coil from the other side, or we're hitting the loop from the other side, I think. But you know, what's the maximum value of cosine plus sine? And work it out, maybe do the calculus or whatever. It's going to be, I think, at 45 degrees, cosine plus sine is a maximum, and the maximum would be 2 times square root of 2 over 2. So maximum value would be square root of 2. And I think we're in that arrangement here. This is kind of like, you know, like, I'm trying to say, what's the image I'm trying to go for here? So there's the area, but if you're approaching something along a certain direction, what's maybe more relevant is what's the area that I see from my angle of view. Maybe almost like, it's not a great example with the corner here, but like if a door is open a little bit, maybe not a door that draws shut, but is open a little bit, like, you know, like it might not be open that much from your view. And a good one would be, and I'm going to do this here, I think, I'm going to use this. And I don't think you guys are going to be able to see this on there, but we can try, especially since I can't really angle the camera. But maybe I'll just try to show what I'm doing here. Okay, yeah, I don't think you'll be able to see it. The projector screen there. So I'm going to hold this guy up. This is a certain area, right? It doesn't matter how I hold this. This has a certain area. It's rigid. And I'm just going to kind of hold it in the path of the projector beam. So what's the area? Well, it's whatever these dimensions are, right? What's the area like now, like looking at the shadow? You know what I mean? Like I haven't changed the area, but by holding it at a different angle, it's effectively like the less area. And this would be almost effectively no area, especially if it was a really thin sheet of paper or, you know, sheet of cardstock or something like that. So like this would be, and we could color it, you know, this could be like positive flux into the front face, less and less positive flux, essentially 0 flux. And that would be where the field is skimming along the surface. And then kind of, okay, so I was here, less. And then I start getting negative flux, which is flux into the back face. And I get maximum negative flux. And then I get 0. And if I just rotate this, we could kind of cycle through that. The other one I was thinking of, this is the other one I was thinking of, is, okay. Let's say you're driving your car and it's raining. Or let's say you're in your car and it's raining. But the rain's falling kind of straight downish. And let's say the sun. So you're sitting in your car, you've gotten your car, it just starts to rain as you're sitting in your car, you haven't started driving yet. And you see a couple of drops appearing on the windshield every so often, kind of filling up the windshield. But then maybe you start driving and maybe you kind of like experience like the raindrops hitting more often on the front windshield. Can you imagine what I mean a little bit? And it's like, well, the windshield's like this and the rain's like this, but when the windshield's moving, it's actually kind of like almost maybe presenting more area perpendicular to the rainfall direction than it was while stationary. Or you could kind of contrast maybe in another scenario where don't have the object be moving, but maybe like the side windows on the right are like this, and on the front and the back, but maybe one's getting a lot more rain depending on the tilts of things. So like there's area, but then if we have a rainfall direction, there's area perpendicular to that axis, that direction of view. So we got that there.
Question?
Yep.
If in the example you have up there, if
Oops,
like
wrong one.
the corner instead of a corner was just this weird like sine wave loopy thing, it still had the same like projection area,
Yes.
but it's all the exact influx.
Yes. So what kind of shape were you imagining? I mean, the answer is yes. I'm pretty sure what you're asking, but what kind of shape were you picturing?
Imagine like
let
a
me-
symmetrical silly straw,
Okay.
basically.
Like waving like this, or but anyway. But overall,
Like the same length that way.
yeah. So if you did some kind of wavy, loopy thing, but kind of started here and ended here,
Yeah.
yeah. So what really matter is probably this area here. Even if let's do something else. Let's say we did this. I don't know, like even something like this. Even if like the flux kind of sometimes went through the front and sometimes went through the back, it would overall kind of work out to be just this. But sometimes you could almost have like negative flux through some pieces of that kind of curly Q-ish, and then maybe some negative flux through other ones. But the net would be kind of whatever we see here. I don't know. I didn't mean to make it quite so nice looking. I meant to just kind of do something. Yeah.
Is it still the same if it has like actual loops?
I'm pretty sure. Yeah. Basically, like this would be an integral. Like we should integrate b dot dA, but b is going to be uniform. So I think in all this, we're assuming b is uniform. So then it comes out of the integral, and then you're really just kind of integrating the dAs kind of perpendicular to the magnetic field direction, which is the dot product is going to pluck off the perpendicular component, and you're just going to end up adding up for each little bit of the green wire how much area is perpendicular, and you're going to add that up, and you're going to end up with a summation for total perpendicular area of the loop presented to the magnetic field. And maybe a lot of the in-between details kind of drop out kind of at that point. And then I think we go a little further and we could say, well, let's say everything's just going to be multiplied by 10 centimeters into and out of the board. Well, then it's really just an integral, not so much of area. Now it's really just an integral of distance in this axis in the plane of the board. And if you integrate that, that's just going to be the final position minus the initial position, no matter how you get from the initial position to the final position, which is fairly characteristic of kind of integrals. No matter how you get from here to here, that the integral is, well, I overall took a net 10 steps that way. And whether that was 12 steps that way, come back to, or 15 steps the other way, go forward 25, the net is 10 in a certain direction. So I think essentially anything that's kind of into and out of the board parallel with length 10 centimeters starting there and ending there will have the same perpendicular area and the same flux as this particular L shape. Yeah. And we might imagine kind of rotating that and getting a flux that kind of varies sinusoidally in time, and that'd be interesting because then we can get a EMF that fluctuates sinusoidally in time. Let's look here at the generator diagram. Just wanted to look a little bit at the diagram here. Section 33.7, induced currents, 3 applications. Application 1, generators. There's a photo. Application 2 is transformers. But here's a kind of a schematic diagram for how you might, one of many ways that you could, but kind of the most basic, simplistic, simple way that you could kind of make contact between, you could design your generator and make contact between the rotating coil, make electrical contact between the rotating coil and some fixed pieces of wiring that aren't going to rotate. How are they making contact in this kind of picture here? Let me get in there a little bit closer. So we have a source of magnetic field, a big, like maybe this is a horseshoe magnet and we're kind of wrapping the horseshoe around. And here is a little gap between the north and south poles. Doesn't really matter which one's north and south, just that there's a strong horizontal magnetic field. And the reason I say it doesn't really matter which one's north or south is as we oscillate, as we rotate this guy, we're going to get a fluctuating magnetic field, or sorry, a fluctuating EMF anyways. How are they making contact? They're calling these slip rings. So the slip ring on this end is always making contact with this edge and then this one on this edge. How was contact made, if you guys remember the little hand crank generator with the light bulb from a couple weeks ago in lab before spring break, before fall break? There was some axle that rotated and there was just that little piece of metal kind of resting against it with a little bit of kind of tension holding it against it, but it could rotate pretty freely while making good electrical connection at all times. The other connection at the other end, I don't think we can really see very well in that arrangement, somewhere like underneath all this stuff that's kind of bolted down onto the base. Sometimes people do interesting things with this, and sometimes these are called, I don't know exactly how this term came to be, but commutator rings are kind of names for like, how are you going to make contact between the rotating piece and the fixed piece? And if you do interesting things, in this case, what's the shape of the electromagnetic, the EMF, electromagnetic force? It's a nice kind of full sine wave. I'm going to call that a full sine wave. But sometimes you'll do interesting things where you'll kind of make these half rings. So halfway through the cycle, like which of these guys is connected to one end of the resistor kind of flip-flops, and then you can actually kind of get this where instead of getting this kind of shape, halfway through the cycle as you're maybe about to go to the negative half of the sine wave, you flip which end's connected to which end, and you can kind of get what's called a half wave rectifier. And so it's like you just get kind of the positive voltage, and then you can make that more complicated by kind of making smaller segments, maybe like 4 90-degree segments for your commutator rings. And you could kind of get a little waveform that kind of is just the peak, and as it's dropping, it's just the peak, and it's just the peak. And you could make it a kind of a variety of shapes. You could make it fairly close to something almost steady by kind of just playing around with the connections. And essentially, you're doing the same thing. You're rotating the coil in the magnetic field, but then you're like, how am I going to make connection to what I'm going to call my outputs? And you could do kind of interesting things there. I will see about that. So let's see. I've heard some people either in the chat or yesterday before or after lab kind of talking about either a couple of questions from the homework, either 17 or 36. Is 17 the right problem? Am I saying that right? Is that one of them? I always get the numbers a little bit off. It was 10, 11, 12 in a row. And then 17, 36. Is there one of those that people would be a little more interested in hearing about, 17 or 36? And where's my mouse? Let's see. One or the other, take some votes. I'll say something maybe a little bit about one of them. And I'll basically just say for the purpose, we'll come back and maybe talk about something a little bit like 17 into Monday. What is the focus of number 17? They gave us magnetic field. There's no loop in 17, right? There's no like, rectangular loop or triangular loop. What is there instead? There's a little charged particle sitting somewhere. And what they're asking about for the charged particle, it's a positively charged proton. and they're kind of managing one of 4 locations. And then they want you to find the acceleration of a little charged particle. Well, if you think about it, let's say there was a loop put down. Let's say there was a loop put down, a circular loop that kind of went from A to C. You might get current to flow around the loop one direction or the other. But what is current? Current's moving charge. So you're basically saying, if I do this process of the magnetic field doing whatever the magnetic field's doing here, I'm going to be able to get charges moving, which means at an individual charge by charge level, you're applying forces to charges and getting them to accelerate up to some speed. And then maybe you're providing them with a nice path that says, hey, follow this nice path through the nice conductor. But one of the key ideas, I just want to read this line once or twice, and then we'll do 36 or talk about 36. One of the key ideas in section, or key repeated phrases in section 33.6, induced fields. This diagram's pretty good here. Blue is always magnetic field, right? Yeah, blue in the book is magnetic field, red in the book is electric field. And we're going to start to see into chapter 34 in particular, lots of diagrams that have both magnetic and electric fields. So maybe just kind of get that, remind myself of that. Blue is magnetic field and red is electric field. So what are they doing with the magnetic field? In this diagram, it points into the page with a bunch of X's and it is increasing. So we could imagine putting a circular loop down. What would we say would happen to the current in that circular loop? I would say there's an into the page flux that's getting bigger. Lenz's law says this wants to oppose that by creating out of the page flux. And if I put down a nice conducting path, I do right-hand rule, and current will flow in the direction of basically those red arrows, which here they're labeling electric field, but we're saying current will flow clockwise. But if we kind of think back to what is happening inside of a wire when current's set up, there's an electric field pointing in the direction that the charges are moving, and that electric field is enough to kind of keep them moving, maybe in particular if there's a little bit of resistance that's opposing their motion. So what this is saying is, what happens if you take away the loop and you just have this region of space and you're turning up the magnetic field? You're just turning up the magnetic field into the board greater and greater. And what we're saying is there is a pinwheel shaped electric field being formed because of what you're doing to the magnetic field. And the phrase that they repeat a couple times is this. The conducting loop in the first diagram isn't necessary. The space in which the magnetic field is changing is filled with the pinwheel pattern of induced electric field. It's happening whether or not there's a conducting path to allow the current to flow. So the core idea is when you turn up the magnetic field, all of a sudden this red electric field shows up. And if you stop turning up the magnetic field, the red field goes away to zero. And if that red field's there and then you put down a conductor, that will lead to current flow. But the conductor isn't really needed for the induction to be taking place. It might be needed for us to make it more obvious that something was happening to the field and maybe make it a more helpful like invention or technology, but it's happening whether or not there's a conductor there. And then they talk about calculating the induced field. And I think this would have been the key formula to use to answer number 17. You could answer number 17 pretty directly from this formula. Did people use something like this? You could recreate the logic that led to this, but the scenario they used to derive equation 3326 is essentially the equation, the scenario of number 17. So number 17 asks for what kind of information? Acceleration of a proton. And this is electric field, but electric field times charge is force. Force is mass times acceleration. So if you took this and you scaled it by Q over M, then you'd have an acceleration of a charged particle. Okay, so here's the phrase. Here it is again. Faraday's law in this new form. The new form is up here, where instead of talking about voltage, what are they doing on the left-hand side? They didn't write EMF. They tried to make the electric field more apparent, and apparently that's the correct way to make the connection between voltage and electric field. And instead of putting d phi dt on the right and focusing on flux, they're like, let's make the magnetic field more apparent. And not too surprisingly, what's flux? It's area times magnetic field. So now we can see E on the left and B on the right a little more directly. So they're focusing on the field the changing field and the induced electric field. And then what do they say right here? In this new form, Faraday's law tells us that an induced electric field is present whether there's a conducting loop or not. And then there's one more line I'm looking for. That's not it. That's not it. Where'd it go? I can't find the line, but what it says is more and more, the more you do electromagnetism, the more and more real the electric field and the magnetic field kind of seem to be. They're not just like, at the beginning, they're kind of just helping us calculate forces. I'll find the electric field, and then I'll use the electric field to find the electric force. But the real thing's the force. And in some sense, that's pretty true. But now we're saying a magnetic field can create electric field even when there's no charges around. And they start to kind of seem to have independent, true meaning and reality themselves, not just kind of mathematical visualization tools that help us think through object A applies a force to object B. And that is more or less the idea of Maxwell's equations is the fields are real. Let's focus on the fields. 36, interesting question. You guys remember the setup for 36. It doesn't take too long to describe it, but it's, what is this one? This one gets a little level 3 difficulty rating. A rectangular loop, we know the dimensions are 4 centimeters by 1 centimeter, and it has a very low resistance. So we have a loop of given position and resistance, and it's nearby a source of magnetic field. The source of the magnetic field is the long straight wire carrying 15 amps, a large current this way, leftward. And the question is, what is the induced current in the loop at this instant? And what do they mean by at this instant? Well, if we waited a little bit, the loop would be further away. And that might mean a different flux if we waited a couple seconds. But at this instant, we're moving at 10 meters per second away, and we're 2 centimeters away at the near edge, 3 centimeters away at the high top edge. And we're moving pretty fast. We're moving, 1,000 centimeters per second, but right now we're 2 centimeters away. So anybody want to kind of get us started on this one? Tell us how you would think through. The goal is to find an induced current. It gives us a resistance. So really the goal is maybe to find an induced voltage or EMF and then just divide by that very low resistance to convert it to a current, which will be probably pretty decent size if we divide by 0.02. That's a 50th of an ohm. We don't have any number of windings, so we don't have to multiply by like 50 windings. As same as one for. Anybody want to say how you would kind of go about starting this guy out? I need a little bit of space as I transition to stuff like this. So 1 centimeter, 4 centimeters, 2 centimeters, 1, 4, 2, 1, 4, 2. Very heavy wire. Very heavy wire, so it's big enough to carry a large current, 15 amps. And then we got our response coil. 1, 2, 3. 1, 2, 3, 4. I'm going to say maybe the width is 1 centimeter. The length is 4 centimeters. I'm going to recommend calling this position here. Somebody want to give me a variable name for that?
R.
What's that?
R.
R. Yeah, D, R, L, A.
You might make using derivatives of it.
Yeah, I totally fine with that. So, and this one is 2 centimeters. And then what's the one other piece of information I need to put on here? You ain't sitting still in this arrangement. We're not rotating and seeing the freeze in the picture right now. This guy's in motion. A little bit earlier, he was down here. You know, like maybe a little bit earlier he's here, and a little bit later he's going to be up here. And he's moving pretty fast relative to the other kind of scales of the problem. I'm going to call this V, and this is 10 meters per second, the velocity vector. Do we have a setup to get induction, to get some induced voltage or current? Oh, maybe one more thing. There's a resistance, and all this has a resistance of very low. That's one of the least important pieces of information here. We can just tack that one on at the end. Do we have a scenario to get induction? Do we have a changing magnetic flux? What direction does the magnetic flux point through the loop, and how is it changing? Now, we can answer those two questions pretty quickly without doing any detailed calculations based on all the labeled amounts. What direction is the magnetic flux through that purple loop? That's a chapter 32 thing, right? What is the magnetic field direction and strength due to a long straight wire carrying 15 amps? So magnetic flux by right-hand rule is going to point kind of around the red wire this way, and that's going to be into the board, into the page in the region above the wire of interest. So there's going to be a bunch of X's here. I'm going to try to show this right a little bit. X, 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 maybe something like that. X, X. You know what I'm trying to do here? What am I kind of trying to do in my positioning of my X's? Yeah. What am I trying to kind of show? And then of course it'd be dots here. Dot, 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 dot. But everywhere up here, there's going to be a B, which is in. What am I trying to do with the X's? I'm kind of trying to show visually the fact that we're getting weaker with distance. Flux essentially means, let's put a number with some units to the concept of how many X's pierce the loop. How many arrows are thumped into the target, basically, or poking out of the target. And you know, of course, if we cluster the X's closer together, more of them will fit through the loop. So which direction's the flux or the field or flux are essentially the same direction, although they're not the same quantity. Into the page, what's happening to the flux? Increasing, decreasing, or constant? Getting weaker. So we have a weaker into the page flux, which means the loop's going to respond with more into the page flux to oppose the decrease. It wants to create more of the original stuff. So it's going to create its own magnetic field. This could be called like B1 or B applied. And then there's going to be a secondary or induced magnetic field or response magnetic field. And it is also going to be X. At least inside of the rectangle, it'll be X, because for a coil, it's through the loop one way, wrapping around, but inside of the rectangle, it'll be more X's. So you actually get another field, which is more X's in purple in here, and then there'd be purple dots kind of outside here. But we get X's. In which direction is current going to go around this loop? Clockwise, I think. They're going to get an induced current to go this way, and now we have to figure out how much. Did I do that right? I think so. If I were to put signs to this, I would say that the field is negative, so the flux is negative, but the derivative of the flux is negative times negative, because it's decreasing and into the page. So the derivative is like positive, but then Faraday's law has a minus sign, so the right-hand side of Faraday's law would come out negative, so it says the voltage induced will be negative, and then when you divide that by resistance, the current induced is negative, and what does negative mean? Probably as an orientation that's interpreted as clockwise. Clockwise. So we're going to induce clockwise voltage and current. And now we might want to find how much. How would you guys find how much? Current is EMF over resistance. That's Ohm's law. And EMF, I'll just put a 1 over R minus d phi dt. So that's Ohm's law, or just connection between current and voltage. This is Faraday's law. And maybe this time I'll leave the minus sign in, but I don't really care too much about the signs right now. We figured out it's clockwise. And then what should we do with phi? Well, the magnetic field isn't changing. Oh, sorry. I didn't mean to say that. The magnetic field is changing. Sorry. BA magnetic field essentially is changing, right? The effective magnetic field as experienced by the loop is changing. The dot product will work out really nicely. I'm not going to worry too much about that. Maybe actually I should say, yeah, I think I might say that. And then what's the magnetic field? The area, I'm going to leave in there, d by dt. The magnetic field would be mu naught I over 2 pi I should do integral dA. That's what I should do. Integral dA. And then I'm going to put a variable down here, and I kind of don't want to call it R. Why do I kind of not want to call it R? Because if I'm going to use R to mean the distance to the near edge, I want this to be a variable which can vary from the near edge to the far edge. So maybe I'll call it L. L for length. I have an L. Shoot, I have an L. I will call it H. H. Yes. So what is H? H is going to point to like some point in the middle here. That's going to be H. And it'll vary from R to R plus W, basically. And that'll help me cover the whole thing, cover the entire loop. And then dA could become what? It's the area of this strip. Maybe it could become the area of that strip. Does that sound okay? You could make it every little square patch is your dA, but you might recognize that that entire strip experiences the same strength magnetic field, so we could kind of take it as a piece. So my dA is going to be what I called L times dH. Little small dimension this way, dH, and constant uniform finite magnitude right, or length left to right of L. And then my limits should be something like I'll integrate from R to R plus W. That's one way you could kind of go about this. This isn't the only way, but that's what I would do. I think I would do something like this. And if I do all this, I will get a formula here which involves what kind of stuff? Well, it's going to have R, it's going to have current, it's going to have maybe mu naught, it's going to have L's and W's and R's. And I think I would do that. And is this kind of how people did this? Did you do an integral to kind of get started on number 36? It's a little funky because why are we doing an integral? Because we need to integrate magnetic field to get magnetic flux. But then what do you do once you found magnetic flux according to Faraday's law? After integrating to find the flux, you immediately turn around and Faraday says, now take a derivative. So overall, kind of what happens from start to end? You integrated, and maybe you integrated with respect to like this coordinate, but then you differentiated with respect not to that coordinate, you differentiated with respect to time. And overall, you're going to end up with something a lot like the formula you started with, something a fair amount like constants over h. You're going to end up with something a fair amount like that at the end, but you're going to have picked up a factor of how fast is the vertical direction changing with time. You're going to have picked up a factor of velocity because the integral was with respect to position and the derivatives with respect to time. Anybody want to tell us kind of what you ended up with? I think I'm going to simplify this a little bit. I missed my minus sign. negative. Actually, there should probably be another minus sign because the magnetic field points into the page according to right-hand rule. So if you cared about the pluses and minuses, I would say there's a minus sign in Faraday's law, and right-hand rule says this magnetic field points into the page of strength mu naught I over 2 pi h. So I'll have two minus signs, and mu naught can come out of the integral because it doesn't depend on height. 2 pi are constants with respect to height and time. So I can do mu naught I 2 pi. That r is not a radius. That r is a resistance. And I think I have an L. That's another thing that can come out here. This is a factor of L. Nothing is going to change about L. And I have a derivative. And I have dH. And I have 1 over h. And the limits would be from near edge to far edge. Does that kind of look about right? Now, you might have organized this a bit differently. I think what I probably would have done myself if I were writing this up is I wouldn't have written the d by dt for a while. I would have just done one calculation to get phi, and then said eventually I'll remind myself what I'm supposed to do with phi. I'm supposed to d by dt it. What do you guys get if you integrate 1 over h dh? So here's the integral, natural log, and then you do top endpoint minus bottom endpoint. You basically get natural log r plus w minus natural log r, which you could also write as natural log of the ratio. Does that kind of sound about right? But then what do you do to that? You now start to look, is there anything that's changing with time? Is there anything that's changing with time? What's the only thing that's changing with time about this scenario, about these labels? W's not changing, L's not changing, capital R's not changing, capital I's not changing. What's the thing that's changing? R, or whatever you wanted to call it. And how is R changing with time? dr dt is a velocity, is 10 meters per second. So kind of like a chain rule, you take a derivative of anything in here that depends on time, and the only candidate is r, and then you multiply by dr dt. So it's kind of like the derivative with respect to r, which is kind of like undoing a lot of this, but then times dr dt, which is picking up a v. So everything's going to be kind of proportional to v. All the induced effects will be proportional to v. I'm going to move this kind of over here. How would I do this here? Maybe I'll just leave it in this form.
You can make the I we already know and I1 just so we know they're not the same thing.
Yeah, this is a good idea. I'm trying to find induced I2, and I think I2 will probably be a function of time, whereas I1's a constant. That's helpful. Thank you.
In the equation be like the I of the straight long wire.
Yep. Yeah. I set that up here. I don't think I made it on the screen. I1. Yeah. So you could talk about like kind of applied and induced values. D by dt natural log r plus w minus natural log r. Is that right? Okay, so we just got the natural log by integrating 1 over constant, and now we're going to take the derivative of the natural log and we're going to get 1 over stuff. Not 1 over constant, but 1 over stuff. So this is going to be 1 over r plus w times dr dt minus 1 over r times dr dt. Yeah, maybe. And the dr dt's are what? 10 meters per second. So we picked up, we do some differences between the top endpoint and the bottom endpoint, which still kind of survives the integral derivative process. We get kind of top endpoint minus bottom endpoint, far edge minus near edge. But we picked up dr dt. And it's basically kind of what happened from about here to here. And mu naught I1 2 pi. I'm going to move the 1 over r out front just to make it seem like something very different. I'm doing 1 over resistance times something. I feel better about that. And then what's going to happen here, dr dt is v. So I'm picking up a factor of v. And then what do you get if you do this subtraction? If you got a common denominator, this would be like r over r plus w minus r plus w over r plus w. Yeah. So you kind of get like a negative w, and the negative is probably the clockwise idea. And I don't care too much about the negative. I care about the w. I think I end up getting LW V all over R plus W and a minus sign. And the sign is just the orientation of the calculated current. I think this is pretty much our answer. What in there depends on time? Not the resistance, not the constants, not the bottom wire current, not the dimensions of the loop, not the velocity. I can imagine moving the loop at a steady 10 meters per second. Not W, but the R is at this snapshot in time, at this moment in time, R was 2 centimeters. And, or maybe the near R and the far R. So you get some kind of like averaging kind of going on here a little bit in some sense. Do I just use the near edge and do like R times R? Do I just do the far edge, R plus W times R plus W? And I guess the way it came out, among other ways of writing it, is the product. So what's R? 2 centimeters. What's R plus W? 3 centimeters. Width is 1 centimeter. Length is 4 centimeters. And overall, all of this stuff is dimensionless. What's the value of all that purple stuff? 4 times 1 over 2 times 3. 2/3, I think. All the purple stuff is 4 times 1 over 2 times 2 plus 1. It is 4/6 or 2/3, and that's dimensionless.
You can cancel out the 2 there.
What's that?
You can cancel out the 2.
Like this 2 and this 2? Yeah. Yep. I was kind of thinking of leaving the 2 pi here, but that's kind of true. So now we have, like mu naught and 2 pi. Anyways, at least the pi with the mu naught, because that just gives me a 2 times 10 to the minus 7. Anyways, I think you can kind of do about the rest of this. Not too bad. What kind of number did people get? People get a number either for a voltage, and then you divide the voltage by the very low resistance to get a current. So I'm going to try to do that. Mu naught over 2 pi, that is just 2 times 10 to the minus 7. I'm going to ignore this and just do a voltage right now. Current 1 is 15 amps. V is 10 meters per second. And all the circled purple stuff is 2/3. Okay, 15 times 10 times 2/3. 2/3 of 15 is 10. 10 times 10 is 100. 100 times 2 times 10 to the minus 7 is 2 times 10 to the minus 5. So I got an induced voltage of 2 times 10 to the minus 5. And then we divide by the resistance, which is 2 times 10 to the minus 2. And you get minus 5 divided by negative 2. Minus 5 plus 2 is minus 3. A millivolt? Yes, no?
Yeah.
Maybe. Our induced voltage is 0.02, sorry, not a millivolt, a milliamp. Sorry, a milliamp. Our induced voltage is 0.02 millivolts, and our induced current is 1 milliamp. And if you want, you could call them negative, meaning clockwise.
So as far as transferring amps, it's not incredibly efficient. It's about somewhere along the lines of 100 of what we started with.
Oh, like that, that's what you're saying, yeah, in terms of transferring amps, I see. Yeah, we're using a very large current to get this whole thing going, and our pickup guy isn't helping us out a whole lot. And yeah, yeah. What are other things we can do? You know, obviously, to make this stronger, we could make this faster. Everything's going to kind of be proportional to V. That's going to be a pretty common feature of all this. And I would say in some sense, where do the V's come from? Integrate with respect to position in the dA integral, differentiate with respect to time. And that kind of brings you back to where you started with, but not quite, because you didn't do integral dx, derivative dx, then you're really kind of like back to where you started. You did integral dx, derivative dt. So you kind of are back where you started, multiplied by dx dt, which is multiplied by velocity. And then there could be other things, you know, where you're kind of doing upper limit minus lower limit. And that kind of came out here. We did upper limit 1 over r plus w minus lower limit 1 over r. Another way to maybe kind of organize this is just do the integral for d phi, and you'll get r in there. And then just realize that when taking your derivatives, basically that's kind of up to about here. And then just kind of realize that when taking your derivatives, the only thing that's varying with time is, I think, the parameter we called r. You could kind of do that different ways. Chain rule says take the derivative with respect to r, but then multiply by dr dt, and that'll give you the derivative with respect to t. Does that sound like chain rule? I can take the derivative with respect to r, but r isn't my main variable of differentiation. It's actually t, so then I'll just multiply by the derivative of the inside with respect to time, which is like I'll multiply by a dr dt. And that's v in this case. And I think the directions worked out really well. I want to kind of track the minus signs. Where did each of the minus signs come from? Now, how I would really do this is I would not think about the minus signs at all. I would just do Lenz's law to figure out the direction, and I would kind of ignore minus signs or take absolute values all the way through. But if I wanted to trust this to get the signs, where did each minus sign come from? I just want to kind of track those. Where did this minus sign come from? Faraday's law has a minus sign hardwired into it. Yeah, this minus sign is from Faraday's law. This is Lenz's law's oppose idea. Okay, and there it is, and there it is. Where did this minus sign come from? Now I have two minus signs, even though you can't see that well, but there's this one here. Where did this minus sign come from? What's the magnetic field? I plugged in mu naught I over 2 pi h times a -1. So what does that minus sign mean? I'm calling out of the page positive, and I'm calling into the page negative, and right-hand rule said when I'm above the wire, my magnetic field points into the page. So this was kind of like a direction, meaning into the page as determined via right-hand rule. So that was that minus sign. And two minus signs. Okay, I've got two minus signs so far, and I did some integrals, and then where did this last minus sign come from? This is kind of the third minus sign or final minus sign. Where did that minus sign come from? Top endpoint minus bottom endpoint. But this is a decreasing function. So at the high, and when you input the big input value, you get out something smaller than when you input the small input value. So my subtraction gave me a minus sign. And that was a third minus sign. So one from Faraday's law, one from right-hand rule, which is basically saying the loop is above the wire, not below the wire, kind of. And then the third one was just kind of subtracting things. But I think the third one is essentially the idea that this field is getting weaker with distance. So minus sign from Faraday's law, minus sign because into the page is kind of default called negative, and a minus sign because as we move, we're moving into a region of weaker magnetic field. And that worked out to be an overall minus sign, which we interpret as clockwise. Quite a bit going on there. Some good calc to think through. Yeah. One interesting thing to think of here is somebody, if they really knew what they were doing, they could do this problem even if no one had ever told them, hey, what's the antiderivative of 1 over h? Like, even if it was some function inside, if there was some function inside the integral, you're like, I don't know how to do the integral of that. It kind of wouldn't matter because the next step is to differentiate. So you'd end up back where you started, top endpoint minus bottom endpoint times dr dt, which is v. And it wouldn't really matter how easy or difficult the actual integral was, because it's not asking us for flux, which would involve knowing the hard integral. It's asking us for current or voltage, which is the derivative of the tough thing. So strange little thought there. And we need to really pay attention as we talk about Maxwell's equations to what are the integrals with respect to and what are the derivatives with respect to. There's lots of position derivatives or integrals. There's lots of time derivatives or integrals, especially derivatives. All right. That is 12:30 on this one.
Where do you want that? Professor.
Yeah, let me just look at something for a second. I'm just looking at the units for this. That there. We're putting in a current, we're getting out a current, so everything else should be dimensionless. And the LW, RW, that stuff is dimensionless. So apparently velocity times mu naught divided by resistance is dimensionless. So that's what I'm going to think about and double check, because
Just a little weird.
yeah, not a very common thought like, oh yeah, those are the same units. Mu naught has units of resistance over velocity. Mu naught has units of resistance over velocity. Mu naught has units of resistance over velocity.
I think you're the only person in this room that uses our papers.
Conrad, Titus, Preston, Rockford.